So, the last class we finished ANOVA, if you remember, and in a sense the last class we were ANOVA, we have started building models. I do not know whether you noticed it, we were starting to write a model for our output data, which is yij equals to mu plus tau I plus epsilon ij. So, we have started building models for our data, okay, and that is where we want to pick it up. So, there are two obvious ways of extending ANOVA. One way is, look, in ANOVA we only looked at multiple levels, like multiple treatments. Now, I have not looked at relationships, I have not looked at relationships, correlations. We learnt about correlations, if you remember we learnt about covariance correlation, did we do that, right, multivariate random variables, we did it. But what we did not do is, we could have included correlations in the model. That is a next step to look at how I include interactions among various treatments. That is a natural, that is one way to proceed, okay. The other way to do it is formally do what is a linear model, how a linear model is fit, okay, and then obviously there will be a relation between linear regression and the ANOVA. In the ANOVA, how did you get model parameters, how did you get those equations? So, expectation of sum square treatment, mean square treatment we did, expectation of mean square error, mean square treatment I derived in the class, and then I gave you some simple formulas for calculating y bar, what I call the mean square treatment and mean square total, I gave you some simple formulae, right. How do I derive it, how do I solve for it mathematically, formally, that we have not learned, I just gave you some formulae, right. How do I do it formally is where we can do now. So, one obvious extension is to go after interactions, the other one is to formalize what we have learnt, the linear models formally, and then see how linear models are obtained or developed, and then move on to interactions, okay. So, we will do the latter, we will first look at the formal way of developing linear models, okay, and then use that to go after interactions. In between we will also learn as an extension of linear regression, we will like do logistic regression also, and then move on to come back to including interactions, you understand. So, now we are taking a formal path, doing the linear regression, building linear models, then we will build models for discrete data as well, that is logistic regression, and then come back and start looking at how to identify or include interactions in the model, clear. That is a detour we are taking now, it is not a detour, it is one path. The other path, natural path, is to go on doing what I call including interactions, etc. One second folks, but that is not going to help, okay, that is not going to help basically because you will not know the theoretical foundation, okay. So, let us do this formally. So, today we will do what is known as linear regression, and specifically today the jargon they give us, it is called supervised learning, it is a part of the overall machine learning tools, okay. So, before we go into linear regression etc., I know this is, as I said, why do you build models and where does these models become useful? These are all methods called learning methods. Why do you learn? Why an algorithm should learn? Where is learning here? Predict, learn to predict, okay. But what is learning? Is there an algorithm required to calculate a payroll? Your salary as an MTech, do you require an algorithm that learns to calculate payroll? It is a fixed equation, force equal to mass into acceleration. Is there anything to learn there for the algorithm to adapt or learn? No. So, when we talk about learning or developing data driven models like linear regression, logistic regression or any other models, okay, that are driven using data, the reason where we learn is very simple. We have solution that changes in time, basically a stochastic process or a random process. We never worry about developing learning algorithms or models, I mean data driven models usually for deterministic cases. What is there in an equation? If you know f equals to ma, that equation is sufficed, done. But when you, why do you want to build a linear regression model? Why do you want a linear regression model for the data you collect? Uncertainties, variations, right? Even if you do the experiment under same condition, the experiment is random and therefore the outcome you get is not fixed. Those are situations where you predominantly think about algorithms that can learn from data, and usually the solutions are changes in time. So, things change in time, the randomness changes over time. So, your algorithms have to adapt, that is again learning comes into picture. Okay. And of course, there are cases where human expertise cannot be explained even. Let us say you are so to give you an example in biomedical, you have seen radiologists look at the image versus you look at the image, very different. How do I capture radiologists expertise? Is it fixed? Is radiologist expertise fixed across various radiologists? So, you go to one clinic versus other, will there not be difference? So, there is a difference in expertise, right. If I want to build a model to understand or to capture the radiologist's expertise, can it be an equation based? Certainly not, because things are going to vary. Then can it be just the humans can explain it very simple? If you ask the radiologist why did you come up with the conclusion, will he be able to explain everything, do you think? Ask yourself, if you take a mobile and then you hear the other person's voice, can you not identify if it is known person even without looking at the number? Your close friend or your family members, you will be able to identify. How do you do it? So, human expertise cannot be explained, even though we do it day to day, it cannot be explained. So, these are places where machine learning and modeling, data driven models comes into picture. So, how to capture the radiologist expert, that is a model, a data driven model or feature driven model which you have to pick up. Okay. So, these are where learning comes into picture, and when we talk about learning, when we talk about building models for data from data, please keep in mind we are only interested in learning general models for particular examples. Okay. So, if I am building a linear regression model, I am not building it for the sake of explaining this particular data that is of absolutely no use to me, because already output is there, input is there, what is there to build a model? I am building it to generalize, therefore I could use it for prediction and various purposes. Okay. So, when we talk about learning, what are we learning? We are learning generalized models. We are trying to build general models from particular examples. Okay. I have a sample from which I want to develop a model that can work for, not for the sample but for the population. That is the whole idea. Okay. So, that is what when we talk about learning models. Of course, data is cheap, information is expensive. So, building models is not an easy task. Okay. So, the other thing is, can you build a model of the end process or the population? Not really. You can never model the reality accurately, but that is what not we are interested in. What are we interested in? We are interested in building models that are good and useful approximations. So, if you talk in biomedical and if you want to understand drug, what to say, drug specificity or drug efficacy, the model you could build could be very complex. Like what? Like how it affects every piece of the body, and then you can start building a very detailed model which will never end. But what is your objective? Whether it works or does not work. If the efficacy is the only concern, then what I could do, I can simply conduct experiments, build a simple model and then say this is the model for X drug and this is the same model for Y for the same underlying disease. Just to build from a simple model from the data, that will suffice the purpose. That is not explaining the entire operation of the drug as a whole. which is not what we are interested in. What are we interested in? We are interested in seeing whether this drug is effective or not. So, build models that are only good for the purpose. Do not build a complicated model trying to explain the entire process, which is not most of the time required. Okay. So, we will only focus on models for particular use case, okay, objective. So, I will not get into this thing. So, when you talk about model building, what are the things required? Statistics, again we started off with, that is where statistics comes into picture. Statistics for whatever biomedical engineers are in statistics, it plays a major role because you are only talking of building a model from a sample. So, that is where statistics plays a role. The other one that plays a major role is optimization when you build models. We will also see that whatever models we build, an objective is involved. As I said, objective of what? Prediction, whatever it may be. In our simple case, when I gave you for how did we come up with mean as the best answer for prediction? When you wanted to minimize squared error, that is my objective. When you want to minimize my absolute error, median became the answer. Now, minimizing the absolute error is my objective. So, usually an objective is involved and you want to minimize or maximize the subjective, and that is where optimization comes into picture. How do I objective? So, in the mean squared case it was simple. How did I optimize? I just did a calculus derivative, which is what we will do here. But suppose if I give you 10 variables instead of y equals to mx, if I give you y equals to m1 x1 plus m2 x2 plus m3 x3 plus m4 x4, will you do still calculus or is it a better way to do? Okay. And these are all simple objectives. Suppose I have a complicated objective function, then it may not be easy to take derivation, differentiation at all. How do I do it? So, optimization also plays a key role in modeling apart from statistics. And then when it comes to implementation, computer science plays a role. We will not be worried about that part. Okay. Implementation part is usually computer science comes into how to design efficient algorithms, so that the objective can be minimized in a shorter span of time. This is where when you build large models, like today you would have heard about large language models, LLMs, or you talk about very deep networks, computer science plays a very important role because you want to model it faster. So, you all have heard of ChatGPT, I am sure. How many parameters are there? 150 million parameters are there. Now, if you want to optimize these parameters or weights, if you run on without optimizing your algorithm using using the science of computation, you will never optimize it, right. So, that is where computer science plays a role, clear. So, that is what machine learning comprises of, building models. You have optimization, you have stats, you have computer science. These three are the key ingredients for building better models. And before we delve into just linear regression, I wanted to give you an overview because these are things which we will look at in your biomedical area. So, there are at least four major classifications. Today we have 5, in fact we have what is semi supervised as well, and then transformer learning, self supervised learning. But there are at least 4 categories, today with the advancements we have 5 categories. So, first one of this, what you could do with data. Here we are building models, statistics, right, but we are looking at a bigger umbrella, statistics for biomedical engineers. So, we do not need to restrict ourselves to linear models or just supervised learning. So, what if I give a data, what are the kind of questions? Let us say I give you a question of developing a drug for COVID. How would somebody would have addressed this problem? Let us say forget MRI, MRI is a very new technique now. If I want to develop a drug for COVID, vaccine for COVID, drug as in vaccine for COVID. How would you start? COVID is there, COVID was there and still there, okay. It was affecting people, and the development of a what I call drugs treatment, as well as managing the symptoms, reducing the symptoms, and vaccine is as of utmost priority. See, if I look at this current COVID virus and then say, look, how does the pathway of viruses? Is there a drug already existing for the same? What am I doing? I am doing associations. This virus behaves in a certain fashion. What is the similar pathway followed by other viruses? And is there an effective way to, if I know the ways to block the other virus, can I try the same for this virus as well? Make sense? This is the first thing somebody, no, I am not asking any super duper, this is the first thing somebody with common sense will start thinking, right. I do not know about Y has a pathway, Y is novel, but I know that Y has a similar pathway as X. Can I use X's idea to for X, the drug used for X and drug used for Y, can I use it on Y? That is what association is. So, we are trying to do first thing in our life day to day is do association analysis, right. You can think of in many cases. So, when somebody has a diabetic, next thing what they ask is check is for what? Hypertension, because the pathways are similar, because each of them influence, right. So, if you have to give you an idea, this is in biomedical. So, if you just go to a supermarket, where is rice located? In a supermarket, where will be the rice located? Last. It is universal actually, even if you go to anywhere in the world, it will be like that. Where are chocolates located? Near the counter, to entice you. Where is eggs will be located most likely? Eggs. It will be along with bread, closer to bread. Why? Breakfast items, right. Associations, right. Basically, how a supermarket is designed is simply based on associations, right. You go to vegetables are located on location, and if you go to all this junk foods will be in one location, because if you go to junk food then they will give you more options, right. So, the essentials will be at the last, but all essentials will be sitting together, because if you reach the last, you know that they know that you are looking for essentials. So, they will give you rice, oil, all of them will be closer together, associations, right. And if you look at even ads at your age, what ads will you receive? Will you receive ad for buying property? No. Women, they will target what? Cosmetics, especially at the young age. Men, sports goods, right, if you would have noticed. At my age, none of them, both of them does not interest me. I would look for property, right, and that is the ad precisely you will get, right. So, associations. Credit cards, what kind of, again credit cards designing at if the target audience is youth, the credit card, what will be of interest to you guys? If you are, what benefits will you look for in a credit card if you are given? Will you look for airport lounge access? Movie tickets, right. You will look for movie tickets, and you look it for Zomato, Swiggy, right. Neither of them interest me at this age. I would look out for airport lounge access, 16 international access, right. I will not look at domestic access anyway, right. So, different, and that design, how is it? Associations, right. So, that is one area where we have machine learning algorithms try to learn the patterns in the data, that is association analysis. Then the second part, the second broad category is what we call it as supervised learning, okay, where there is a teacher who tells what is right and what is wrong and let the model learn the right and wrong in the training data set. So, that is where only in supervised we have something called as training and test, because in training data the teacher is there instructing what is right and what is wrong. So, our linear regression etc. will fall under supervised learning, where there is a teacher in the training data giving the answer, so that the model learns about the data set and it can perform well in the exam. Basically like giving answers in your tutorials and asking to do well in the exams, that is the same idea, that is supervised learning. And supervised learning itself is of two types. So, that is what we will look at both in this course. First one is on classification, that is like categorical, good, bad, ugly, your Netflix ratings, right, 1, 2, 3, 4, 5 stars, all of them are. So, Netflix does what, Netflix or Prime does what, recommends for you. So, now the way it is done is two parts, association and classification. This is where power comes of machine learning, power comes, modeling data power comes when you start doing multiple things. First thing is you are only one user for Netflix, Netflix or Prime has multiple thousand if not multiple lakh users. Now you would have rated a certain movie in some way, can I first associate you with a particular group based on your ratings and based on their ratings, how the movie is rated, can I actually associate, that is association, okay. That is a typical example of associating with a group, a particular person with a group, that is association analysis. Followed by what? Followed by prediction of this movie, you may give a highest rating, let us say 5 is high, I am predicting that you may give 5 for this particular movie. Even if I associate in a particular group, that group will be larger and you would have some thousands of movies in that group, they may be watching. If I provide you with thousands of recommendations, will you care to even look at? 30 seconds is the attention span, I should catch you if I can, right, in 30 seconds. So, what should I give you? I should give you out of 1000 what is the best 4 or 5 I think will be of interest to you, right. That is prediction or classification, right. I am going to predict out of these 1000 movies which one you will give the highest rating, and that is a discrete prediction, that is not a continuous variable, it is only stars 1, 2, 3, 4 or 5, those are the only 5 possibilities, right. I have to pick up predict for these movies, he will give the maximum rating and then pick up the top 5 and present it to you, and that is how it is presented, right. So, that is called recommender systems, today very popular, but that does combinations of multiple. So, classification is like predicting the outcomes, like classifying sad or beautiful, sad or happy face versus sad face versus classifying the ratings etc. That is belongs to the classification problem. Again you build a model using a training data set where there is a teacher and the test data set is left, and this is where we will be looking at today, which is regression or prediction, typically predicting a continuous variable. This is doing a continuous variable, okay. Then we have something called as unsupervised learning, where there is, of course you should have expected, there is no teacher, it is simply like association, grouping of things, clustering of things, right. That is based on similarity. How do you say two shapes are similar? These are questions which we have most often in biomedical as well. Why? Because in images you want to see the similarities and then that similarities help make decisions in CT images. So, they say size of this image, this axis, and then say this is slightly extended. Image analysis, similarity mapping, similarity analysis, that is all unsupervised learning. There is no right or wrong again, it is all grouping of things together, right. So if you look at an EEG data, we know normal, we know abnormal. Why? Comparison, grouping based on similarity of features. Same with ECG, grouping based on similarity, right. Remember, there is nothing like exactly correct heartbeat. What is correct? All of us, will we have the same heartbeat now? Definitely no, but I suppose most of us fall under the normal category. How do I say that? Features of EEG, if you take ECG, if you take and match, it will more or less be similar, grouping, right. That is unsupervised learning. And today something very popular is called semi supervised, which combines both unsupervised and supervised learning. This simple example in biomedical is again coming back to radiologist. Suppose I want to develop an algorithm for automatically detecting cancers. Let us say breast cancer is one where lot of effort has gone in. So I want mammography to be automated. Now if I want that to do, who should develop the training data set? Who should give the ground truth answers? Radiologist. And typically remember, when you develop these kind of complex models, see, linear models are simpler and lesser number of parameters. The moment you do non-linear models, the parameters are going to be high, and the complex the problem is, the number of models will go high. Now if you want to build a model with more number of parameters, do you think ChatGPT, what is the training data set? Will it be thousands? You cannot have 1000 data point to train million parameters. If it is million, better be tens of million is your training data. Now can I ask tens of million data to be trained by a radiologist to give a ground truth? Will the doctor sit and label for you? No. So today this is where the entire machine learning algorithms are moving towards. The supervised learning is a thing of the past. Why? Because I won't get labels from experts. Subject matters experts are difficult to catch, and if you ask them to label tens or thousands of data, they are not going to provide you labels. So doctors are not going to label for you. It is not going to happen if you ask them tens of thousands. So how do I intelligently ask for labeling, right? So suppose suppose how do I start doing that is where this semi supervised learning is. You are trying to label it intelligently. What do? I first do unsupervised, group the data, whatever data is collected, group them. Now where will be the issues? Only at the boundary points, overlapping of groups, there will be confusion. If it is a cluster center or a group center, you just need one label from the doctor. If the cluster center is, let us say, no metastasis or no tumors, then anything nearby that is most likely no metastasis, the same label. And if there is another group which is far away and then says, look, this is definitely malignant, then we know the answer is malignant within that group. Where will be the confusion? At the borders. So intelligently ask for labels from the subject matter expertise. This is the algorithm today being deployed at multiple locations. So if you look at MD Anderson, right, so the scan images have to be definitely seen by the machine learning algorithm. That algorithm recommends to the doctor, and the doctor, if he supersedes the learning algorithm's result, then he has to give a reason why, and the learning algorithm again learns it back. Okay, this is today operational. I am talking about this is being done in MD Anderson, where not only for images, any recommendation to the by the doctor to the patient is initially assessed by machine learning algorithm. The learning algorithm then provides the recommendation, its own recommendation. The doctor looks at the recommendation, either he goes with it or he supersedes it. If he supersedes it, then he has to tell why he is superseding. Therefore, the machine learning algorithm can learn and give better recommendations. This is already in practice today, okay, and that is where interactive learning comes into picture, which is what is called as semi supervised learning. It is a combination of both supervised and unsupervised learning, which is called semi supervised, very useful in biomedical, especially in drug development. So, I was working with a company for a new drug development, a cancer drug development. Experiments are very costly, experiments are costly, drug development experiments are the costliest, okay. Now, initially you may have million or billion molecules that you may want to screen. Finally, what is, how many drugs you develop? From a million to 1. How do I accelerate? If I start exploring million, I would become a pauper, probably I will never develop in life. How do I narrow down? That is where today machine learning is making a big revolution. All this data driven model is making a revolution in this domain. So, if you know proper machine learning, especially in pharma, today you are sitting in a gold mine, because everybody wants to accelerate this drug development cycle. Usually it is 20 years, today we want to make it to less than 5 years, okay. And how do I do it? How do I screen the molecules initially faster based on associations, right, and not only on associations. This is where semi supervised comes into picture. I have a whole bunch of data, failure data, which has not worked, which has not labeled, but I know the molecule's properties. You understand, drug molecule properties we have, but we do not know whether it will work or not, whether it has worked or not, because people would have either done experiments and not reported, failures people do not report. So, people would have tried the molecule and either they would have not succeeded or they would not have even tried it. We do not know, because there is no labels. So, you have a huge set of unlabeled data and a very small set of labeled data. How do I combine these both to develop a model? That is a big question in pharma industry. You have a big set of unlabeled data where you know the molecular structures, everything, but I do not know whether it has worked or not. Typically toxicity is a problem, cytotoxicity. When you talk about drug molecules, cytotoxicity becomes difficulty, I mean an important parameter. Half life, you have to predict the half life of the drug properly, right, and you should have an idea about not just cytotoxicity for cells, but for the particular various organs, liver, hemato, that is very important, because liver is the one organ which is used for taking waste and then cleaning it out, right. So, liver toxicity, and you also talk about efficacy, specificity, right. So, there are various parameters when you look at. Now, all of them people would not have labeled, they would have labeled only for the successful drug, but if you want to develop a new drug, then that drug is already there. If you copy it, what will come new? Nothing will come out new. So, you have to screen for various molecules, but you will not have all this information. You only will have what? The drug structure, the molecular structure and those details. So, how do I actually use this million of unlabeled data with a small set of labeled data to develop a drug? That is what today the semi supervised and other thing, and that is where if you look at Google etc. has been putting lot of money. They have their own networks to even today talk about protein unfolding etc., protein folding, how does a protein fold etc., predictions, that is what they do, many networks do that. So, that is a big problem in pharma industry, and that is where the semi supervised comes in very handy, okay. Then we finally have reinforcement learning. If you would have played games, how do you think you build strategies, how do you think a computer plays against you? Today if you play against chess against computers, is it easy to win? Level 1 you will easy. Suppose if I put it level 10, it can even give competition to Vishwanath Anand and others, right. In fact, even in 2000, early 2000 I guess, Garry Kasparov was won by Deep Blue. he lost to Deep Blue, which is a machine learning algorithm that is based on reinforcement, building strategies. So, these algorithms are used to build strategies. It is neither supervised nor unsupervised. There is a teacher, but the teacher will not tell you every step is right or wrong. The teacher will only tell you, give you a reward when you built a strategy. When your strategy is wrong, there is a penalty, okay, but only after you build a strategy. Remember, have you played the strategy games? Have you built any strategy games played? So, if you are building houses, etc., not every move is important, but the overall strategy is reflected somewhere. Not every move in the game is equally important, right. Even as a novice, if you play chess, do you think every step is important? May be important for an expert, but for a novice we do not play every step is important. After a certain step we know, we understand the opponent's strategy and then start modifying. That is where the key stage where one should get a reward or punishment. That is what these algorithms do, which is called as the reinforcement algorithms for building strategies. So, these are the various applications of machine learning algorithms, okay, in broad, and as I said, our biomedical engineering requires all of these techniques, okay, and in fact advanced. So, today any new algorithm comes in, that comes first to biomedical engineering domain, because the problem is so rich, as I said, from million to one molecule, a grand challenge, right. So, today we will only talk about regression, okay. So, before we go into regression, a quick recap on covariance and correlation. So, we have learned what is a covariance. It is a linear relationship between two random variables, which is expectation of x minus mu x into y minus mu y, okay. It is a linear relationship and it will be pretty useful in developing linear models, okay. I have shown you this, was done last class, I mean previously we have done this, then we have normalized it, that is your normalized covariance, which is correlation divided by the square root of variances, and this is how you compute from data, okay. And interpreting covariance greater than 0, they are positively, all of them are linearly related, okay, and less than 0 they are negatively, inversely linearly related, and equal to 0 linearly independent, they are linearly independent. This is also called as Pearson's correlation coefficient, okay. It is a dimensionless quantity, okay. So, now let us get into regression analysis, okay. So, we will look at it in the next class.